Okay, thanks. I'm the last talk of the day, so hopefully it's interesting. I tried to make it so it's more of an overview of computation at the edge, acceleration and introduction to methods and challenges, and look at some future directions that we as circuit designers, but also as a larger community, could look into. So my talk is fairly simple in terms of agenda, just motivation, like why would we do mixed signal to begin with for computation, and then look at a couple different methods that are currently out there and being actively researched, some of them for quite some time, and then of course concluding. So there is a large and diverse application space for sensors, ranging from some of the things we saw today, accelerometers with human activity recognition, all the way up to autonomous driving. And, you may have just single sensor inference in this case, but then in autonomous driving case, you're talking about multiple sensors that are fused together, radars, lidars, imagers. And so these inference tasks have very diverse requirements. And I'm sure as many of you know in this in the audience, but ranging from human activity recognition, we may have very small networks that are only doing tens of thousands of operations per inference for human activity recognition, but for autonomous driving, it may be up in the billions. And so that can mean much different hardware. Then in terms of accuracy, no one really cares exactly how far you walked. Maybe you really care how many steps you took. But you don't really need to have that accurate of a network to figure out that you're walking. Well, in the other case, if I'm sitting in an autonomous car, I want it to be damn sure that it's not going to pull out into a busy road without knowing that it's safe. So accuracy is very important, but then it depends on task. And then, of course, inferences per second, or inferences per millisecond. This is the thing, task speed. We're not fast. Humans aren't fast. So for human activity recognition, seconds, checking every couple seconds to see if you're still walking, or maybe you decide to start running for some reason. Yeah, that's probably good enough. But for autonomous driving, you may be wanting to do this much quicker rate. And then you end up with orders of magnitude of energy or power range in this case, going from nanowatts to hundreds of watts, depending on what you're doing. And system cost too. A lot of the sensors that we make at Bosch are, cost a few cents. And so you don't want to spend a lot of silicon area on inference. But maybe then for autonomous driving, that's not the case, because this may be costing tens of thousands of dollars if you're paying for your autonomous driving in your Tesla, for instance. So yeah, inference complexity, accuracy, power, energy, throughput, they vary quite widely. And so what's the real benefit of doing analog compute? Well, we have a lot of predecessors that have been looking at this. Vitos is always referenced. SNR and compute energy are linear related, at least as he derived this in this paper back in 1990. And so there's a theoretical advantage to processing in analog as long as you're doing low precision. Right? If you want to do high precision, then we see in this plot that we probably want to be looking more in the digital domain. But maybe we can take advantage of some things in order to, still use analog to do that. Now, of course, you can argue digital benefits from technology scaling, but then you can play some tricks, calibration, maybe do feature computation in the analog domain to try to get that benefit back and keep this window open. So that's really a challenge, but then at the end of the day, there's also requirements. In academia, they're different than there are in industry. Maybe At least I feel they are. But anyway, there is that challenge there, and so like I just want to show like a sensor architecture. Like this could be autonomous drive, just a very hypothetical architecture, but where you have multiple sensors that are maybe fused together with a whole system. They may be doing classification on individual sensors themselves. They may be doing it however you want, but at the end of the day, they may be also transmitting high fidelity data to the host system, and then they're not doing classification there. So it's really a question of like what you're trying to do. So where does it make sense? What you're trying to do? That's the thing that I have to try to answer when I'm doing work, especially if we're trying to stick something on inertial sensors, or we're trying to build something that accelerates like autonomous driving classification algorithm. So for the smaller sensors where you may have a single sensor that you're just doing classification, analog to information, which I guess that graph that I showed earlier with the resolution or SNR versus power, you should read Marianne Verhelst's paper if you haven't before. It's a very nice paper. That is basically taking analog sensor inputs, maybe doing computation of the analog signals directly to extract features, and then doing inference, eventually going to digital. And then, of course, in-memory compute, let's say you want to fuse a bunch of sensors together. In this case, it's most practical for these systems to be transmitting digital output data. And so then you still may want to try to take advantage of the analog mixed signal in terms of energy. For instance, like if you think about an autonomous system and you're running an electric car, you don't want to be burning 3,000 watts in your computer that's in your trunk to do autonomous driving, because you want your electric vehicle battery to last so you can drive a few hundred miles. So this is where the two areas are kind of diverged, but I'll talk about a little bit of both. So the interesting part of analog to information is that if you have a lot of work that's been done up front and you know what your signals look like, you can engineer or identify pre-trained features that you want to extract from the signal. Right? For instance, in these graphs right here, you may just want to capture the peak of the signal. In that case, then your feature rate, the bandwidth, it may be much less than what you actually need to do to sample the actual signal. And so this is already an advantage. And then furthermore, if those features are perhaps you don't have as much dynamic range or SNR that you need for those, you can then say you can get some benefits. You can reduce ADC power. You can and that power reduction can be fairly significant. And then not only that, if the output of this ADC, let's say you've now gone from, let's say, a very high number of bits, high precision, to maybe like a few bits, then your back-end digital processing, since you're only working at a very low bit precision, not only is it lower power, it's also lower area. So these are some benefits of doing this. Whoops, sorry. Yeah, okay. So I wanted to point out just a couple examples of this. This is some work that my group and Professor Boris Merman, one of his students, was working with us a couple years ago, and this is for a CMOS image sensor, and it was trying to extract edge features from the image sensor. So instead of doing an ADC, just a full CIS with a full resolution ADC, and then doing inference in the background, then it's trying to do some feature extraction first, and then maybe redesigning the ADC to do something else, and then doing background classification after that. Just as an example, in the log gradient, basically is taking the ratios of the horizontal and the vertical pixels. It reads it out of the sensor array, the pixel array, stores it analogically, and then takes a ratio of that and these ratio to digital DACs and outputs only a few bits. So you're only getting a few bits coming out of this, but you're able to do good edge detection and use this for classification. So this is an example of that. Then another example is, in the microphone space, where you have there's known features called Millceptrum coefficients, where they're basically just a nonlinear FFT spaced nonlinearly like your ear, and you want to measure the power in that spectrum. Well, you can do that, of course, with analog bandpass filters. Do something like this, or the empath switch cap filter, where you can basically control the center frequencies, you can control the Q, you can control the bandwidth as well, therefore. And then you have a nonlinearity after that you're doing, using that to, like a mixer in this case, so that you can actually do FFT. In this case, then, you can reduce the ADC bandwidth by a fair amount, and also the effective number of bits you need. Like a standard microphone may be operating somewhere in 20 kilohertz, and like somewhere in the order of 18 bits. So that can save you a lot of power. So then I thought, well, okay, what's the apples to apples comparison here? And there is a couple of works that I just pulled out of literature to see, does analog features help you versus digital features? And I think the answer is it maybe. All right, so that's the thing. First of all, you can see that the analog filter bank is about 8x lower power than the digital one, and it also has more filters in it. It's 32 versus 20 for the digital one. But what about the overall system performance? That's the one thing I wonder about, right? So, and in that case, then it's a little bit less clear, because these are both systems are optimized for low power, right? They're not, and for feature extraction, they're not, and basically classification, they're not trying to do, high fidelity microphone output, measuring at 18 bits. So then if we look at this, then, the ADC powers are even better for the digital one, right? And then we also see that overall, just the analog was only 2x better. So to me, it basically says that, if you have smart people in the room and they sit there and try to figure this out, you can do some optimization. I think you saw a lot of work from, or a lot of chips from Masha yesterday, where I think she's doing, at least most of the architectures I saw, she's doing, an ADC and then all digital, right? I don't see the analog feature extraction, but I do think that there is a place for it. But the question is, like, how flexible it is. And then the last thing I want to mention, I will talk about this again later on, but hardware-aware training. So if we want to reduce the precision of the front end and then the bit precision of our devices, and we want to then perform inference, normally I guess it depends on your type of your system, but if you're using TensorFlow or PyTorch or something like this, you're going to need to have to model your system when you do training. And because these systems introduce error. And the nice thing about AI, at least training, is it's an optimization. And so even though if you have error in your system, you can optimize it so it goes away to some degree by training the weights, by training the system. There are some some interesting things that I've seen. You know, if you make the system too simple, if you make the precision too low, then your models may blow up and actually get bigger, and then your efficiency may get worse. So it's not always an easy game to play, but it's something you can do to try to push down energy, push down power, and gain back accuracy of these inference systems. But you need to have someone who's well versed in this to do it, right? It's not that's something in industry I think we're missing. So a custom software tool chain is a must and a need for these kind of systems. So overall, you know, there's a lot of benefits for this. I think always-on applications, especially if you know the features very well and things like that, you can think about this. And of course, reduced ADC complexity in the design, and then reduced digital complexity. You know, of course, it works with a lot of different sensors there. I think the challenges are really, you know, what features are matter, because once you do these designs, they're kind of fixed, right? They're not, you can't change them. They may be somewhat tunable, but they're really not flexible. And so this is where it comes into the industry thing. You know, I go and try to sell this to my customers internally, and they say, well, hey, what if I want to change the algorithm to this, this, and this? And then I say, well, the heck with this, and I can't do it, right? Because they basically don't want to do it. So sometimes it's a hard sell, but it's you really have to show the benefits of it. And so I think that there is where you have to really have well-known and features in the system has to be well-defined before you like go and do it. And the software tool chain, as I mentioned, you need a specialized tool chain for this. It's not just a simple thing. And then also coming back to reality with industry, yeah, I can make this design, but then they're going to tell me, hey, I still want to output the 18 bits. All right, so now I have to change my front-end VGA, I have to change my ADC, I might have to bypass the filters, I have to do all this stuff, and I have to stick it all in there. And oh, by the way, you can't use any area to do this extra stuff because the chip only costs a few cents. So this is sometimes a challenge that we have. So now moving on to in-memory compute, which is mostly where I've been working the last couple years. This is where the sensor interface, you know, may not be able to be changed. Like we have some, you know, gyro designs where it's like basically all digital in the front end. They cancel quadrature, and so you could, of course, try to tap into it in the analog domain earlier and try to extract features, but you know, quadrature can be orders of magnitude bigger than the rotation rate signal, and so I'm not sure that you'd be able to train a network to be able to pull that out. That might be some interesting research to see. And so there is one case, and then with autonomous driving, I think it's very simple sensor fusion. The interfaces have to be digital. And so there, when you want to accelerate something, you probably need to use in-memory compute. So, you know, in-memory compute, the workhorse that you're trying to, or what you're trying to do is do multiply and accumulates or dot products. That's the biggest thing. For instance, if you're trying to do this inference problem, you're trying to like do an image classification. Say, what kind of car is that? Oh, it's an XC90. Well, I have a 5-stage CNN, maybe a ResNet 50 that's doing this. The majority of this is convolutions. Of course, there's other types of functions as well, but a majority of the operations here are convolutions. And so, you know, that's where we want to see if we can do some mixed signal design to minimize the power of that. And again, coming back to that same plot that I showed, well, the only way we do this is efficiency is to do inaccurate max. All right, so we don't want to accurately calculate them. We want to be doing them inaccurately. All right, so I like this plot a lot. I don't know if anyone in the community here has seen this, but this has come from Tsinghua University. and it's a plot of throughput versus power for neural network accelerators. It's an interactive plot. You can sort it, so you can sort it by industry and by like computational precision, all different kinds of things. So it's kind of fun to look at. I guess you're getting these slides afterwards, or if you can just drop me a line, I can give you this link. But here is on this plot are basically lines of constant efficiency. So, and often they're reporting efficiency in terms of teraops per second per watt. And what we see is, I just put some examples here. You can actually hover over these if you get this, and you can see, you can try to find NVIDIA, and you can try to find all the other ones you want. But what we see is that most of the industry is below this 10 tops per watt line. There's a few of them are out there, a little higher. But that's sort of the limitation there. And what is causing that limitation? Well, there's a lot of different things. It's highly architecturally dependent. This picture is from a book chapter that Professor Merman just published maybe, I think, a year ago or so. But I wanted to use it just as a kind of an example of what's limiting energy. So let's say that you're doing a calculation, and this is a Mac accelerator, and you have an array of these. In each one of these Mac accelerators, you have some memory, a register file, and you have multiply and an addition functions here. And so if you want to do a multiply and an add, then that costs you about 230 femtojoules to do in 28 nanometer CMOS. And then let's say you need to move an activation, move a weight, take a partial product, move it to the next register file, take a partial product, move it. I actually take the output of your multiplication and accumulate, write it back to the register file, then take that and move it to the next guy. That takes energy. And so that may take 4 movements to the register file, which is costing you 10 femtojoules per bit times 8 times 4, and then you get something like this, 275 femtojoules just to do a Mac. And so that ends up giving you about 3.6 tops per watt. Now, of course, you can do a lot of things to try to minimize this, but in the end of the day, what in-memory compute does for you is it does this multiplication, summation, and analog, which can be very efficient, right, at low precision. You can have the weights stored here in this, and they don't need to be moved, so you don't need to read it out for actually out of the off-chip DRAM, assuming your model fits on the chip, which is a big assumption. And then the other thing is that these partial products, they don't need to be stored in memory. They can just be all summed up together if you're doing a large Mac operation. And then, of course, you need to somehow take that. You need to do an ADC conversion, but I'll talk about that in a minute. But yeah, that's kind of the advantage of it. So now let's add everyone else in this plot. And we see that a lot of the high performers are in memory compute. For instance, like this one here is, even though they say it's digital, I guess I take I disagree with that, because it's basically SRAM based with current summation. So I think part of it's mixed signal at the minimum. Anyway, I should contact them and see if they want to change it. But anyway, we can see that we're getting the thousands of tops per watt here, but at limited computational precision. So that means your inputs to your CNN have very low bit width, and your weights for your CNN are very low bit width as well. So I just wanted to make a note, because I've noticed often, and even in ISSCC and a lot of other conferences, metrics get mixed together and often are reported in the most advantageous point. And so this is something I just wanted to mention, that we don't do this, Because, for instance, efficiency, which is basically number of operations per second divided by power, this is 1 over energy, which is just tops per watt. 1 over 1 picojoule is 1 tops per watt. And area efficiency is operations per second divided by area, and that's number of operations per second divided by millimeters squared. But then, okay, let's see, throughput can be maximized by running at the max operating clock frequency and the highest power supply. And then efficiency is much better at lower clock frequency and lower power supply. Maybe you get lower power when you do that, and then you report your throughput at this and your efficiency at that, and that's in your title of your talk. So I would caution the people to not do this, because I don't think that's actually fair in terms of like what your actual performance is. And then area efficiency, tops per millimeter squared. This is highly dependent on what you decide what your accelerator size is, right? So if you keep something out of your calculation, you may look much better there. So, and then finally, oftentimes if you start reading these papers, efficiency can be reported at different bit precisions. And so I think this is also architecturally dependent, but for instance, if you report efficiency at 8-bit precision for weights and activations, that's going to be up to 64x lower than if you reported it at 1-bit weight and 1-bit activation. And oftentimes I see that in papers it's not very clear, what that is, and it's difficult to know, what the performances of the device is because of that. And then one more comment on performance metrics. Really, if you're designing a full accelerator, the best way to report performance metrics is energy per inference, like how much it costs per inference end to end for your entire system. And then also consider your throughput, like how many inferences you can do per second. And then of course area or silicon cost you can look at. And then, you can see this computation, but really what you want is that the best way to benchmark also is to do a known data set and a known model if possible, so that you can do an apples to apples comparison to other people's work. Other than that, it's difficult to do comparisons because this is a very large area and there's tons of ways you can do these things. It's difficult to compare. All right, so then how in-memory compute works. I'm doing a very simple overview of this, but basically it's a crossbar array network, and it has some unit elements in these crossbar arrays. And these unit elements can be transistors, resistors, they can be capacitors, and they can be implemented with non-volatile memory. They can be implemented with SRAM and an additional device like a capacitor or a resistor, or they can be ROM based too. There's multiple different ways to do that, but the idea is then to store these weights locally. So that's the weight stationary part. And the interfaces they can vary. They can be just digital or they can be specialized. For instance, the activations can be specialized digital to analog converters. It can be like a full voltage output based DAC that you're driving, like for instance X1, or it could be like pulse width modulated. So you could have a 4-bit input activation and you get 4 bits with different pulse widths. And then you're storing charge on these columns. All right, so then so the column readout also needs to be an analog to digital converter. And there's been a couple of publications. Actually, I was working on making this whole thing into a SAR. And I wrote a patent on it like about 3 or 4 years ago, and then there was a ton of publications at ISSCC and other places that they already did the idea. So I guess everyone was thinking the same way. But you could reconfigure these unit elements also as your computational thing that convert this charge on this column back to digital. So as I mentioned, the summation on this column, it can be current based or charge based. A lot of the most efficient ones are charge based. So even if you're using resistance, often what you're doing is you're sending a pulse and you're pre-charging this bit line to some value and then pulling off some charge from it for a short amount of time, and then this bit line is just got a stored summation in charge. It can be challenging to do this in current, but people have been doing that too. So now I just wanted to make a comment about non-volatile memory, just because, you know, I've also suffered the pain of trying to get access to non-volatile memory, and maybe other people have also. But you need to develop a full IP solution if you want to do in-memory compute with non-volatile memory. And so, for instance, the memory cell itself, if you want to store multi-bit weights in it, so you're really excited about it, and you got a flash cell, and you want to put 8 bits in each flash cell, and you're going to drive the gate, and so that's what you're going to do. Where are you going to get that flash? How are you going to do it? Who's going to program it for you? Who's going to come up with the algorithms to do that for you? That gets a bit challenging, right? So you end up either having to do it all yourself, or you don't. And then, for instance, RAM is an interesting case. You know, most RAM is optimized for fast read speed, and so the resistances are fairly low. But if you're doing some kind of in-memory compute, you may not actually want the resistances to be so small, especially if you're doing this pulsed type of thing where you're storing a finite amount of charge on a column, and you're trying to just, and you want to sum up like 256 different things. You don't want to pull off a lot of charge. You want high resistance. And so this comes down to the fact that you may end up doing semiconductor development to actually be doing this stuff. And some people are in position to do that. Myself, I am not. That's one comment on that. The other comment is that if you also want to do non-volatile memory or just take memory IP and try to take it and do it, it's not so simple. The row drivers here usually are activating all the rows at once in in-memory compute. Typical memory, you only activate one at a time. So that's something. And then if you take a typical IP memory from wherever you get it, and its column readout, maybe sense amps, those sense amps are not really designed for what you need to do for in-memory compute. So overall, in-memory compute development with non-volatile memory, it is very promising in terms of, very compact. You can have a very high number of bits, but it's not easy to do because it requires access at all levels of the non-volatile memory chain in order to actually implement it. So, what we're working on is this SRAM based in-memory compute, and in this case it's pretty scalable for most processes. It doesn't need non-volatile memory, but then the weights are stored locally, maybe in a local SRAM here, and but then you only have 1-bit digital multiplication. So we're not doing analog multiplication. We can do digital multiplication, and then we do summation on these columns. In this case, charge, but you also can do current-based approaches. So if you want to do multi-bit, so right now I've only shown 1 bit, but let's say if you wanted to scale something like this to multi-bit, what you need to do is you need to add columns. So if you have 8-bit design, then you would need 8 columns. Each column would be storing column 1 would be storing the MSB for each weight, then the MSB -1, etc., all the way to the LSB. And then in addition, if you want to do something like this and you want to make it fairly compact, you may want to do some kind of bit serial approach where you feed your activations in one at a time. And then those activations then get summed on these nodes. And then you need to do some scaling and accumulation afterwards to get your full MAC computation. And you have to scale it by the bit precision or location of each column. So if this is the MSB, then it's like 2 to the 7 all the way to the column all the way on the right hand side, which would be just scaled by 1. So finally, if you want to do a multi or a parallel MAC, you just add rows. So each one of these is calculating one 8-bit MAC, just this computation here. And then if you want to do a multiple of them, you add rows like this, and then you sum them in the analog domain, and then of course you have to do some sort of ADC conversion. Okay, so coming back again to precision, I just wanted to share this because I think at least it's nice to have it out there and know about this, is that when you start summing up like 1-bit max, so each one in the column, you have an array here, and let's say you have 256 rows, and each one of these does a 1-bit computation. And so what is the SNR of this analog signal coming out here? It's going to be close to 8 bits. All right, so as you increase the number of rows in a in-memory compute array, if you want to really get the full fidelity output, you need to increase the ADC resolution in order to do that. But then here's where there's a couple of different things an approximate compute come in. One is that if you consider the weights and the activations as random, and maybe some distribution, in this case just a uniform distribution, what you can see is that the actual output precision is less than the 8 bits most of the time, and you can actually calculate or keep full precision of what your output is with a lower number of bit ADC. And not only that, you can also use hardware-aware training to even scale the ADC resolution lower to push power down in these, because what we want to do is reduce energy per MAC. So we don't need to convert the full dynamic range, but there may be some interesting issues with like offset of where this distribution is. So you could think of maybe a scaling ADC or something like this would you require. So if you only need to convert a few bits or 6 bits, but you need to move where you're converting it to like a ranging ADC, may be something interesting. Okay, what about energy per compute? So one of the big benefits of in-memory compute is that you're amortizing the cost of doing this analog to digital conversion over the number of MACs that you're doing. All right, so basically, if you're doing 256 parallel MACs, then your ADC energy that you paid to do this conversion is divided by that number per MAC. That's your ADC conversion cost. And then, of course, you have some cost for each in-memory compute computation. So you can get like a very rough estimate of ADC energy or overall energy this way. If you use like the ADC survey, you can do a curve fit and get the very best case just to see where you could get with that. And like, okay, so if I have 256 MACs and I have 8-bit ADC, then I can get about 5 femtojoules per MAC, and so that's about 395 tops per watt, but at 1 bit, right? So that's decent. It's pretty good. and better than what you can do in digital, but it's also much less precision. So here's a example of exactly this type of an approach. So Jason Lee, I think one of his students was doing this. Yeah, it's SRAM with charge sharing summation. The computational precision is, activations are 2 bits, weights are 1 bit. It's bit serial, it's 256 rows. It's SRAM with capacitance, and so it's doing summation and charge on each column. And in order to increase density, it's putting the mom caps, sitting them on top of the SRAM cells. So that's that, and he's using a flash ADC at each output of the column, and he's using 4 bits, not 8. All right, so so if I plug in my numbers for their equation, that simple equation I did, I get something like 493 tops per watt, something like that. It's pretty close to what he reports. Actually, he's got higher than that. So, that was just a rough calculation, so maybe that's possible. And so, but the thing that I think is more interesting is looking at what the overall macro or PE does, and that's around 35 tops per watt, and that's okay. That's a 2 bits resolution for activations and 1 bit for weights. I like his paper because it also points out a few things about efficiency. So in memory compute, so I think we went over the fact that, larger arrays, you amortize energy of the ADC. You want to have big MAC arrays in memory compute. But then efficiency varies with utilization. Like how much of the MAC array are you using to do your compute? And then, so you may have certain parts of a model where you have fairly small kernels, you have fairly small max number of parallel max you're doing, and your efficiency is going to go down quite a bit because you're activating this entire array and you're doing a very small compute. It may not even fit in it, for that matter. So he has a plot of efficiency versus number, how the PEs are utilized, which I think is a good thing to show. Other thing is interesting is that if your data set and your model, so if you use a simpler problem, and maybe I think you use a C410 for both, but if you use a simpler model, you may be able to fit that on a chip, right? Because in-memory compute allows you to have a lot of weights, right? But then your overall efficiency could be pretty high, but as soon as you start using larger models and go off chip, you basically crater in terms of efficiency. So this is something that's important to understand when you're looking at in-memory compute. It is only as good as like the overall system and how you design it. If you're really having to pull data off of outside DRAMs or things like that, then you're going to start pushing performance down, and all the work you did to try to make this very highly efficient MAC computation is not going to be the dominant thing there. So, and then finally, the last thing I think is interesting, and I think a lot of papers do this, but looking at like what your loss is in precision when you use like full floating point versus like only 2-bit activation and 1-bit weights. And of course you need to do hardware aware training to get this accuracy back up to like in orders of like losing a few percent in inference accuracy. So in summary, there's quite a number of benefits for in-memory compute. You've got the low precision, so you can get lower compute energy than digital. You can have much higher density, and it of course depends on how you do the design, but even with an SRAM design you can get fairly high density Mac computations, and then of course then smaller area, which means lower chip cost for you. And then the one thing that we're also interested in as a company is a potential, if we can do very highly efficient Macs, and we may want to use a larger process node, right? We don't want to use the 5 nanometer, 3 nanometer processes to do this acceleration, because frankly it costs too much, right? So maybe there's an advantage there. And then, of course, weight stationary compute, lower data movement, that's always a positive. Now, the challenges are hardware training, right? That's required to recover the accuracy loss from your reduced precision. If you want to do non-volatile memory, then you need to go and get yourself a partner that's going to work with you on that and is going to open up the semiconductor process to you to maybe make changes. That's challenging. Throughput is an interesting one, and people don't talk too much about it, but if you actually have a D to A converter and A to D converters here, if they take multiple clocks to do your computation, that hits your throughput. All right, so some people only put a flash ADC, for instance, on the column, and some people have SAR ADC here. So it's a trade-off on what you're trying to do. If you're trying to do low throughput, super low power, you may want to do SAR ADC. If you're doing something that's higher end, then you may not. Utilization, as I mentioned before, very important, and system architecture as well, super important. You may do all this work trying to do this cool in-memory compute design, then you go and stick it in a larger system, and something else dominates, and it's really not the thing that you should have been working on in the first place. So future directions is something that I think is very important, and I think is hardware and software co-design. As a community, at least my needs, I would like to have some sort of thing sitting in my CAD tools or something like that I could just enable modeling of these systems. All right, so this is something for our community to try to drive and push. I think everyone is building their own little ecosystems to try to get this thing done. But if we really want to make it so that it's like something in the industry, we need something that somebody to step up and do that. AI-assisted analog front ends, I think, could be interesting, looking at error correction or detection or tuning of the analog with an AI model in the back end. Maybe even thinking about hybrid modeling, like physics-based AI, where you're modeling maybe your front end and then trying to predict what the output can be. So that's something interesting. Then, as I mentioned earlier, reconfigurable analog to information front ends. If you really want to make it so that it's a product, maybe it's so it's really, it depends if you're going to like high mass production for something or it's just a very specialized sensor. But I know, like from my experience at Bosch, I'm not going to get away with like designing an analog to information front end that's like super low number of bits and small and done all this analog feature extraction without also being able to provide the full number of bits coming out as well. And so it could be an interesting area of research to try to see, how you combine these two in a smart way. And then I think Marianne Verhelst, she had a paper a couple of years ago in ISSCC, but I think I haven't seen much more about this, but I think hybrid accelerator systems that are combining in-memory compute with smaller digital acceleration is something that could be interesting because, as I said, depending on the model and the computational load, you can schedule your your computation so that when you have very large parallel max, you use the in-memory compute array, and when you have smaller compute problems, you just use a digital one, and try to get best of both worlds. So yeah, that's it. I'd like to thank a bunch of people, but appreciate it. And I've got some references at the end if when we have this. I guess we're distributing these so people can use that to look it up.